Moving on to the introduction. Firstly, the research aims to enhance power quality (PQ) in contemporary electrical power infrastructures by examining causes, effective mitigation measures, and simulating various PQ scenarios using MATLAB. A methodical approach is employed, starting with identifying PQ issues and ending with implementing solutions. And then three PQ states are simulated, which is steady state, disturbance, and post mitigation recovery. Next, the objectives. Firstly, is to understand the causes and effects of three different power quality issues and simulate and evaluate them using MATLAB. Secondly, to assess the efficacy of several mitigation strategies for these PQ problems while making sure that they adhere to international standards. Lastly, to enhance the academic and practical understanding of power quality management by documenting the findings in a thorough report that includes real citations, results, figures, and explanations. Nextly, the chosen power quality disturbances in our project. Firstly, voltage sag. Voltage sag is a temporary reduction in RMS voltage. Next, voltage swell. Voltage swell is a temporary increase in the RMS voltage. And for the last one, harmonic distortion, which is refers to deviations from the ideal sinusoidal waveform of the power supply voltage or current.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Fikri bin Muhammad Nonaski and number matric AE200004. Alright, today I will explain about our methodology for this project. Okay, for the theory applied, the voltage surge, which is the IPS, temporary drops in voltage caused by sudden loads, fault or lightning, managed with voltage regulators and UPSs. Voltage swells, temporary voltage increases due to the faults, capacitive switchings, or load drops, managed with power conditioners and SPDs. And for harmonic distortion, distortion of the normal sinusoidal wave caused by non-sinusoidal loads like computers and variable frequencies drives, managed with filters to remove specific harmonic frequencies. Okay, next, for this project, we use the MATLAB Simulink. We use the MATLAB Simulink to model power quality issues. MATLAB also is a tool that let us simulate and analyze engineering problems, and it also includes Simulink, which helps us draw and simulate the circuits. For overvoltage scenario, we create a transmission line circuit in Simulink to see how a surge protection device handles overvoltage. For task 2, we will draw and simulate a distribution circuit in Simulink to observe harmonic distortion before and after applying a filter. Okay, for the flowchart for this project, okay, here the flowchart for the project. First, we start. Then the input is write the literature review, and next we design and draw the circuit in MATLAB Simulink. And next, we have the condition, which is in the run. When the run we run the simulations, if the error is detected, it will go back to the before condition and the before input, which is in the circuit simulation. And if it is no error detected, and then we can observe the output result, and we analyze the result, and it's the end of the project.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Arman Hajimi bin Ibrahim. So I will continue for the result for this project. So the figure shows an setup in MATLAB Simulink software that illustrate an electrical power distribution system with components to manage and monitor voltage level. Starting with an 11 kilovolt power source, power flows into an 11 kilovolt bus bar and then 1 megavolt transformer, which sets down the voltage to 0.4 kV for lower voltage applications. This power is further distributed via another busbar. A three-phase breaker protects the system by interrupting electricity flow during faults. The power then reaches bus 2 to supply the load, representing the device using the electricity. Additionally, a dynamic voltage restorer (DVR) between bus 1 and bus 2 corrects voltage sags or swells, ensuring stable voltage level. The figure illustrates the result for voltage sag in three-phase system at 11 kV and 0.4 kV, with each plot showing three sinusoidal signals for the three phases. The sag occurs around 0.25 seconds, marked by a reduction in waveform amplitude, and lasts until about 0.35 seconds. This temporary drop in voltage magnitude caused by short circuit overloads or a sudden load change affect both high voltage and low voltage levels, similarly indicating a disturbance in the power system impacting both distribution levels. After 0.35 seconds, the system returns to normal after DVR correct the issue. So next, the figure shows a voltage swell in a three-phase system at 11 kV and 0.4 kV. Each plot displays three sinusoidal signals for the three phases. From 0.25 to 0.35 seconds, the waveform's amplitude significantly increases, indicating a transient voltage swell. After this interval, the voltage returns to a normal after the DVR corrects the issue. The swell affects both voltage levels, similarly suggesting a temporary event causing the voltage to rise momentarily.
Assalamualaikum, my name is Muhammad Faiz Hakim Mimir Ahmad, magic number AE200026. Now I will continue to explain about the result and finding. Next, we provide a simulating diagram represent a three-phase rectifier system. It consists of a three-phase AC source connected to a universal bridge rectifier through a three-phase VI measurement block. The rectifier DC output from the universal bridge is filtered using an LC filter, which is inductor and capacitor in series, before feeding the load. The scope connected in the circuit is used to visualize the voltage and current output. In this context, the term harmonic distortion describes how the existence of harmonic produced by the rectification process causes the voltage and current waveform to divide from their ideal sinusoidal pattern. The diode or transistor that make up the universal bridge rectifier by nature produce non-sinusoidal current with a high harmonic content. This harmonic may result in electromagnetic interference, heating of the electric component, and problem with power quality. The LC filter was designed to attenuate this harmonic, smoothing the output DC waveform to reduce distortion and improve overall power quality. Measurement and analysis tools such as the one shown in the diagram are essential for assessing the extent of harmonic distortion and the effectiveness of the filtering. Okay, next is the result. Figure show two plot illustrating the analysis of harmonic distortion in a signal. The top plot show a time domain waveform of the signal where the select portion for past Fourier transform, which is FFT analysis, is highlighted in red. They are harmonic present because the waveform look to be somewhat distorted sinusoidal signal. The result of the FFT analysis are plotted at the bottom, displaying the signal harmonic spectrum. The x-axis represents the harmonic order, which is multiple of fundamental frequency in 60 Hz, and the y-axis shows the magnitude of each harmonic as a percentage of the fundamental frequency magnitude. The fundamental frequency has the highest magnitude and several harmonic, particularly the second, fourth, and the higher order harmonic. are present with a significant magnitude. The total harmonic distortion, which is THD, is calculated to be 18.77%, indicating a substantial level of harmonic content relative to the fundamental frequency.
Okay, we go to the conclusion of the project. Power quality issues like voltage sags, voltage swells, and harmonic distortion can affect electrical systems, and voltages bring brief drops in voltage caused by things like short circuits or large machines starting up, which can make sensitive equipment malfunction. While voltage swells are short increases in voltage that happen when large loads are suddenly switched off or due to the fault in the system, potentially damaging the equipment. To prevent these issues, we use device like uninterruptible power supplies, which is UPS, voltage regulators, and surge protectors. For harmonic distortion occurs when the electrical waveform gets distorted due to harmonics, often caused by electronic devices like rectifiers and variable frequency drives. And can lead to the overheating of transformers and motors, equipment malfunction, and increased power losses. To manage harmonic distortion, filters and harmonic compensators are used along with careful electrical system planning. So, by addressing this issue will ensure smooth operation, longer equipment life, and lower maintenance costs. So,